Hello everyone, in today's video I'm going to be showing you how to use the gradient descent technique and how to work with that. So we are going to start with scratch and let's dive into it. So I'm going to use Visual Studio Code at first and also Google. so um, so first of all I'm going to open the desmos calculator. Then I'm going to use also the topics I've discussed in my channel already. So let's dive into my channel, view your channel, and then playlists. So as you can see, I have this playlist right now here. So if you are not familiar with three topics in this playlist, how can I get into playlist directly? Okay, so if you are not familiar with all of these three topics, you need to watch it. This is definitely will help you to understand this topic, because all the thing I'll explain in this topic they come from these three topics. Okay, so you need to know them. First derivatives, then point slope line, a visualized version, and then chain rule. So this is you just you must watch it. So anyways, then I'm going to change the theme in Desmos, so reverse contrast. Then we're going to call x x and then y axis y. So as you can see, we got here this coordinates. Then what I'm going to use is also mirror. So I'm going to open the mirror. I think that's it. The last thing I'll use the Google Docs, and the reason is because I need to create team board. The reason because I need to explain you what is the gradient descent. So let's dive into it. I'm going to open my Google Docs. Where is it? It's here, and then math. Okay. Inside here I have the topic about the derivatives, standard deviation, and then gradient descent. Okay. So what is the gradient descent? Gradient descent is an optimization algorithm for finding a local minima for differentiable functions. In other words, it is the algorithm which can find a local minima for the function, and this function must be differentiable. What means by the local minima? It means zero for this for at this point this is zero for this function, like something like that. But I'll explain a bit more about it. So in order to apply gradient descent technique in back propagation step, we must have a loss function, and that's true. We're not diving into it right now. Just need to know. Let's now create some of the functions. At first, I want to create the parabolic function. It's going to be x raised to the power of 2. So this is the parabolic function, right? Then I'm going to plot the point at 2, so x is equal to 2, and then according to the f of x, we will get the corresponding value. So I'm going to say x1 is equal to 2, and then y1 is equal to f of x1, which is just simply logical. So now we got our f of x1, so which is obviously 4, because 2 in the power of 2 is 4. And then what I'm going to do is I'm going to plot them. So I'm going to say x1, then comma, and then y1. So now we got our point here. And this is pretty much cool. So I want to see right now what is the derivative of the parabolic function. And as we know from the previous videos, which I've explained in that playlist I showed you before, the formula, the derivative of the parabolic function is simply 2x. So this is our this is our derivative of the parabolic function. And of course, if I'll say the derivative is equal to, of course, d of x, which is just for the sake of simplicity, f and then dash here and then x, I'm going to get the same line. So I'm going to just delete this because this is represents the derivative. So any point on the graph of x2 is going to be the derivative is 2x. Just we will take the x value. So this is our derivative, and I'm gonna make it slight less I will make opacity lower, 0.5, and then I'll make it thickness lower. Yeah, so I made it, and probably so. Yeah, so it looks fine. So now we have it here, and the question is, remember the topic about the slope point line, which I suppose that you have watched from my channel or from other channels. So to make the line through this line, we're going to use this formula, which we've explored already in previous tutorials. So y minus y1, which is y1 is here, is equal to x minus x1. So as you can see, we got the line to this point, and whatever I will put this point on this parabola, it's gonna be dependent of this point. Okay. So now the question is, first, how can I make a slope? And another question is, can't we just say that y is equal to x minus x1 plus y1? And of course we can say this because it's simply like the mathematics rules. So it's gonna work the same way and perfectly. So, but for the sake of simplicity, I'll just use the standard ones, which is y minus y1 is equal to x minus x1. Now the question here is that how can we create the slope which will be corresponded to the derivative? So, like basically, what is the derivative? Again, recalling the definition of the derivative, it can be simply the slope of the tangent line. So if it is the slope of the tangent line, it basically will go all the way along the parabola function. Again, if you totally don't understand what I'm talking right now about, you need to watch the previous videos and you will get into it, because this video will be also included in the playlist of the diving deeply into the mathematical concept of the neural networks. So to make this, what we're going to use, we're going to simply use the derivative. So as you can see, we have the slope. Before that, like so we can say the slope is 2, and we can say the slope is 3, and whatsoever. So it will be like that. But for knowing that we need the slope corresponding to our parabola, which is going to be the slope of the tangent line, I'm going to use this d, which is the derivative. So I'm going to say d and take x of and take the derivative of the x of 1. So the derivative of x of 1 is going to be equal simply 4. And the reason is because 2 multiplied by 2 is going to be 4. And to check this out, we can just put it out and we got 4, as you can see. If we will take, for example, 1, so I'll zoom in a bit. If we will take 1, we will get 2 as the derivative. So let's check this out. And for 1, we got exactly 2. So this is how it works, just 2x. Now the question here is that how does the gradient descent work? Now knowing that we've made everything what we were about to do, now we need to now use the mirror. So let's just imagine that probably you have you have $100. So you have $100. And you probably gave to your friend this $100. So your friend is here like happy, like thank you for this $100. Sorry for my drawing skills. And he has this like bunch of money here, so which is dollars. Okay. Now the question here is. How fast will he return this money? And probably he will return it to you in 1 day. So 1 day passed and he returned you $98. And so you recall what you gave him, and you remember that you gave him $100, but he returned you $98. So what was the mistake of your friend? The mistake was in $2. So he forgot to return last $2. That sum may be full. So now you are going to your friend. So let's imagine that this is you. You just a bit bigger, and you a bit mad on him that he returned you. Just like he returned you just $98. So you are asking him, hey friend, why did you return me $98? And he's saying, well, you gave me $98, but you remember that you gave him $100. And you are saying him, well, you are mistaken. I gave you $100. So the question here, what is the mistake here? The mistake is $2. Like I gave you $100. your mistake is $2 because you forgot to return them. So knowing this, we can say 100 minus 89 is going to result 2. And what is 2? 2 is our error or mistake, miscalculation or offset of what we gave to our friend. So in order to use the gradient descendants in this situation, in this situation, we're going to go into the desmos and say well, so we have 2 here, okay? So this is our mistake error. So our x is 2. This is our error. How can we optimize it that our mistake may be 0? This is the question actually here. So in order to understand how it works, we need to go into our Visual Studio Code. So first we're going to say that our error is equal simply to 2. He forgot to return $2. So $2 or like that, okay? So actually we can say $2 and in brackets. So now the question is, how can we optimize it that mistake may be 0? So that our friend does not mistaken at all. So his mistake is 0. It means he gave us what we gave to him. Now, in order to calculate this, we're going to recall what is the derivative of the parabolic function. And this is actually, right now, I'm explaining the technique, how can we apply the gradient descent. So, of course, so how can we apply the gradient descent? And now I'll explain the technique here. So first, what we're going to say is that we're going to take the derivative of our function. So on our function, it applies to here. So 2 is corresponding to 4 on our parabolic function. So what is the derivative of the parabolic function? It's going to be def derivative and x it takes, and then it returns 2 multiplied by x, which is totally correct. So our derivative of the parabolic function is 2x. And this is again the technique of the gradient descent. So first we take the derivatives, the derivative of our parabolic function. And you may say, what is our parabolic function? Let's say that this is our loss function, okay? So this is our loss function. And we may say like, well, if it is our loss function, now we need to apply our error to our loss function. What is our loss from our error? So, and the parabolic function says that your loss is 4 because the parabola rise the number into the power of 2. So in order to do this, we're going to say that our loss from our error, which is a bit different term, is going to be 2 raised in the power of 2. Or we can say even so, def parabolic function is taking x and return you x raised in the power of 2. So we can say that our loss is equal to our parabolic function close the dictionary, and our parabolic function receives error, okay? So basically our parabolic function a bit increase our error because our actual error is 2, but in order to use the gradient descent we need to use this parabolic function, or you can use another functions depending of you, but for the sake of simplicity for the first video of gradient descent I'm going to use that parabolic function. So we're taking this error and we kind of raise it a bit, so our error becomes more bigger. It becomes bigger. But now we have our loss. So now we can exactly say that our loss is just simply x raised in the power of 2. And now again, what is our loss? So our loss x raised in the power of 2. So now this corresponds to our whole parabola, okay? And the reason why it corresponds is because now we raised our error in the power of 2. It means that now we've created kind of parabolic function because we calculated the parabola y-axis, right? So we calculated what is the y-axis for the 2 and the parabolic function, and we created an error, so we created this point. So our error and then our parabola results to this point. So this is our point of loss, okay? Point of our error, kind of. So now the question here is, what shall we do next? And I'm going to create a loop for I in a range of, let's say for the first time 5, and then we will say that our loop is going to take first the derivative of our error, okay? Of our error. The question is, what's going to be the derivative of our error? So the derivative of our error is going to be dE, which represents the error, is going to be derivative taking error. Okay, so now we took our error here. So now we have the derivative of our error, and the question is, how can we bestly optimize our error to make it equal to 0? And to make it work, what we are about to do is to say that right now our error is 2, and then we're going to say that error minus equal to the error, and then multiplied by 0.01 or 0.1 just simply. So what is the 0.1? This is the also learning rate, and we can say like first learning rate. This is how it looks like, and then oh no, learning rate, I forgot. Usually in practice we just call it ln, which represents learning rate. Okay, ln is equal to 0.1. Or whatever, you can change it in a way of your problem. Like what is your problem, you change it correspondingly. So this technique we will explore a bit more. So this is our learning rate, and we're going to multiply our learning rate by our derivative, and I'll just in a minute explain why. So we're going to multiply it by this, and then I'm going to print what is our error becomes 2. So now let's run it, and as you can see, our error becomes lower and lower and lower and lower and lower. So it means that our error becomes like explicitly low. How did we get this result? And what if we wouldn't use the learning rate? So let's get back to here. So as you can see, the derivative of our x of 1 is equal to 4. And the question here is, how can we bestly optimize it using the mathematical operations to result it to 0? And if you would say, well, it is just simply derivative minus x1 minus the derivative. If we would do so, what is our derivative again? It's 4. So we would say 2 minus 4. It results here, and we have the same problem. We have the error minus 2. Now, it is not 0, and it becomes even worse here. So the question here is, how can we bestly optimize it? And what if we would just take our 4 and would say that our 4 is multiplied by 0.1? So if our 4 multiplied by 0.1, it becomes 0.4. So if I would say 0.4, it becomes lower than it was before, but it becomes nearer to the 0. Again, if we would just use 4, it does not become closer to 0. But if we would use our learning rate, multiplying it by 0.1, which is the gradient descent technique, it becomes lower. So again, we have 2 right now. And what if we would take our derivative and multiply it by the learning rate? If we would do so, now we would get 0.4, and 2 minus 0.4 becomes lower, and it means it becomes nearer to the 0. So our mistake will become at the end 0. So now let's check what we've made here. As you can see, we got 0.6 here, and now we have 0.6 as well. So I'm going to say first that I'm going to print my error before of this, and then I'm going to print the derivative multiplied by the learning rate and minus before them. So it becomes our subtraction. So now let's clear this, and yeah, of course. Let me say that this is the derivative. Okay. So now let's make it again, and as you can see, first we do 2 minus 0.4, and this is exactly what we did, 2 minus 0.4, and it becomes lower, so our loss becomes lower. So I'm turning back to our story about our friend who borrowed our money. We may say that now our friend shall return to us, like if our error 1.6, now he shall return to us 1.6. Okay. No, sorry for that. He shall return to us 0.4. So now our friend shall give us 0.4, minus 0.4, which is actually not that much correct, because he shall return us 2, not 0.4. I mean, when we get minus 0.4, we are telling that right now our 98 becomes yeah, I think it shall be plus 0.4 if it becomes 0.4 in such a way. Let me think about it a bit. So in our story, he borrowed $98, and now he shall return us $2, right? So right now we're saying that what is our loss? Our loss became 2.56. Before it was 4, right? Yeah, before it was 4. To you see, let me think about it. Okay, so we may say about this in such a way. So we have our minus 0.4, and what is our minus 0.4? It says that our error was minus 0.4. So right now we are saying our neural network, like gradient descent technique, is saying us that our error right now, before our first step, was 0.4. So right now our friend definitely needs to return us 0.4. This is the definitely he shall return to us. Like, we're not saying yet that he shall return us 2, but he's definitely shall return us 0.4. Like, you see, if we look at here, he shall return us 0.4, but our error is still, our loss is still big. And this is the reason why I've created this loss. I will not use it in the code, but I've made it for the sake of simplicity to explain it how it works here. So our loss is our parabolic function, and it's saying us how bad we are right now. So what our error says is that this value is going to be better if we will subtract 0.4. So our friend is now shall give us $0.4 like 4 cents. Or 40 cents, I think 40, but doesn't matter. So, and our loss saying us that how bad we are right now. So, like saying that our friend shall return to us 0.4, the loss of this is still big. So we are kind of losing our money. So our loss saying us that how bad we are right now. So our prediction that we he shall return to us 0.4 is pretty much bad, and this is what our loss is saying, that this is 2. So when our loss becomes 0, it's saying that we lose 0. Like, our prediction that he shall return to us 2 is definitely correct, because our loss is equal to 0. So this is kind of how it works in a simple example. So now let's check this out. Now, and what I'm going to do next is I'm going to subtract 0.32, and the reason why I'm going to subtract 0.32, because now we have our derivative 3.2, and this is the it's very important to understand that as our x value becomes lower, our derivative becomes also lower, and in such a way we cannot kind of jump out of the 0 to the negative side. So you will get into it a bit later. So now 3.2 we shall multiply by 0.1, which is our learning rate, and multiplying this by our learning rate, we result 0.32. This is what exactly our code resulted. I don't know why it's 6 here at the end, but just never mind about it. So now from our 1.6 we show minus our 0.32. So now doing this minus 0.32, we become slower. our derivative becomes also lower and our loss becomes lower. Again, look at the loss. So our loss was 2.56 and right now it becomes 1.63. So our loss actually is saying that minus 0.4 and minus 0.32 results as 0.72, which is 72 cents or 0.72 dollars. And it is saying like $0.72 is definitely better than was 0.4 because our loss becomes lower. It means that we are losing low money, a less amount of money. So right now our friend shall return us 0.72 instead of 0.4. 0.72 he shall return to us, and our loss is saying that we are going in the right direction. Like our loss becomes lower as you increase how much your friend shall return to you. I hope you got into this idea. So I'm going to do the same time again, and then I'm going to do it at all. Like I'm going to make like 10 iterations then, or 50. So let's make it 10 iterations, and then our next iteration says now we have 1.28, which is exactly 1.28. So right now my x1 is 1.28. If we will zoom a bit, we will see that our point here is 1.28. Okay. We see that this is 1.28, and what I'm going to do is to again subtract the derivative of our point, and this is how our gradient descent works. This is the algorithm which makes iterations, and inside these iterations it takes the derivative, it subtracts this derivatives from our target value, which is x1, to understand what is our error right now, and also multiplies this derivative by our learning rate, because if we want to multiply our derivative by the learning rate, we won't get the good result. Okay, so this is how it works basically. I hope you dive into it, and if you didn't get it, rewatch it again. So now, okay, so now I'm going to do the same thing. I'm going to multiply 2.56 by 0.1. So multiplying this by 0.1 result me 0.256. Okay, so now I shall subtract 256, and again check what is our loss becomes to. So minus 0.256, and our loss becomes lower. Now it's 1, before it was 4. You see, so before we were losing like 400% kind of, right, from our x, because when our x was 2, it was saying that, well, your loss is too big, like your friend shall give you a lot. And now we are going to the 0 again. So what is our gradient descent? It is basically the range. So we get inside the range. Inside this range, we takes the derivative from our error. Okay, so we takes the derivative from this error, and then we subtract this derivative multiplied by the learning rate from our error. So we're subtracting the derivative multiplied by the learning rate from our error, and our error becomes lower, and correspondingly our derivative becomes lower. So and this is the how gradient descent works. I mean, if our derivative wouldn't be lower and it would be always 4, it would always subtract 0.4, and if it would always do so, we would get minus 0.4 minus 0.4 more 0.4, and then again 0.4, and we are already on the negative side. But when it becomes lower, it becomes slower. Like it becomes lower, it becomes slower. A bit rhythm here. I think you got into it. So now knowing this, that our gradient descent is just simply subtracting the derivative multiplied by the learning rate from our error on our loss function, we're going to implement much more iterations to get into it. How much will we get? So as you can see, after 10 iterations, we did just 3, and I mean we did just 4. Yeah. no, 3. We did 3 iterations, and on the third iteration, we already got 1.024, which is almost in 2 times lesser than we were before. Our loss becomes lesser, it means we'll lose less money, okay? So now our friend actually from these calculations shall give us, is going to result 72, and then 72 plus 2 is 92, and then 92 plus 5 is going to result again, yeah, 92 plus 5 is going to result 9c 9. Wait, I'm a bit confused here. Again, so it's 0.4 plus 0.32 results as 0.72. 0.72 is 0.976. 0.976. So right now our friend 0.976. So right now our friend almost shall give us the dollar. So we're asking neural network how bad he is. Like for example, your friend told to your neural network, I mean, to your gradient descent technique, he said like, well, I returned to you 89, and but your gradient descent knows that before he had 100. So your kind of your machine calculates the error, and then from this error it calculates the loss, and then it is calculating it, don't bothering you. So you are kind of relaxed, and then you, at the end of the day, you come to your neural network, and as you are asking like, what did he return and what's the error? Is there an error? And your neural network says, yeah, there is an error. Like he's right now on this like epoch of our gradient descent, he needs to return to you. I mean, he shall return to you $0.976. And as our gradient descent will go more and more by our iteration, at the 10 iterations we already get 0.26. Okay, so in order to calculate this, we can just like sum all these minuses, and this will result the change which we need to do in our x. So in order to calculate this, we just simply need to say that a negative sum. So, and we're saying, of course, underscore, and we're saying that right now this is 0, and negative sum like is equal to minus derivative multiplied by the learning rate. So, and it is basically, does it work? And at the end we can ask, how much shall we change during all these iterations? Of course, I can do like minus 0.4, minus 0.32, and then so on and so on and so on and so on till the end when I need to subtract minus 0.0536 and so ever. Or I can just ask, can you please sum all of them, and I'll just at the one time will subtract them. So let's do so. And at the one time I can subtract 1.7 after 10 iterations. So now I'll remove all of them, and now we got to our loss before. So our gradient descent didn't do any work at all. But if I'll subtract right now this, we got almost to 0. You see how near we are near to 0. And asking our loss, what is our loss right now, is 0.046. And if we'll check this out, this is the same loss, and somehow I didn't get it here. Why didn't I get it here? Oh no, I think I get. Did I? Let me check this out, guys. So we are telling what is our loss. Where do we tell this? Yeah, we didn't tell it anywhere, so we need to check out what is our loss. So we can say like loss parabolic, and then error, and then print our loss. So our print now and then loss right now is equal to let's say like till the 8 number, this also, and then loss, and then now of course I need to use correct syntaxes. Now what's there, I forgot format, if I'm not mistaken, format. So loss, and then let's check what's our loss. It's 0.046, and what's here, it's absolutely the same, even further, because I just a bit shortened it. So as you can see, we have the same loss here and the same loss here. And now let's make 100 iterations, and check this out. After 100 iterations, what our gradient descent is going to tell us. right now our gradient descent tell us that your friend shall give you $1.78 and whatsoever there. So right now our friend shall return to us basically this number, and I'm going to increase the size. Okay, so as you can see, our gradient descent works perfectly fine, and right now our friend shall. Can I take it? Why can't I? Oh, of course. Right now, our friends shall already give us this. So let's make 100 iterations. While we on the work, our gradient descent will calculate it. And when we will go at the evening and we'll ask our gradient descent, what did you get? We're going to say we're going to get something like that. And as you can see at the end, our friend shall return to us something like this. And this is almost $2. Like right now, our loss is just almost zero. Like rounding this, our friend shall return to us $2. Like if you will round this even from here, this will be $2 exactly. And you at the end of the day, you come from your work knowing that your friend told to your gradient descent technique you what did he return to you, and gradient descent technique you some machine inside knew that you borrowed him 100. For probably you put it into the note, and then it checks, well, in the note there was 100, and then he returned 98. Then the mistake there is $2. Of course, it's easy to calculate, but using the gradient descent, you may calculate this as well. So knowing that this mistake is 2, the question here, how can we lower this to make our mistake 0? And knowing this, our gradient descent says that to lower this, you need to make some iterations, multiply the derivative by the learning rate, and subtract it from your error. And at the end, I would say to you that you need to subtract this number also from here, and then our loss. Like if we will do the same things here, like we had 100, then we subtract 89, and then our gradient descent says that you also shall subtract this amount of this number to get the mistake 0. So now we have the mistake 2, and you've asked your gradient descent, what shall I do to make this 0? So I hope, obviously he shall return 2, but the question here is how mathematically, using mathematical concepts, you can explore what shall we do here. So what shall I do here to make it into the 0? I hope you got it. Of course, as the human being, you may say, well, it's obviously 100 minus 89, 88, 98 minus 2 is going to result 0, so our mistake will be 0 if you will just return us this $2. But, if the problem is much more bigger, like if there is tremendous amount of these problems, like 100, 1 million, you will never get out of this. So to using the gradient descent will calculate everything is much more faster than you. So giving him your 1,000 francs to whom you borrowed, the gradient descent will calculate how much each of them needs to return to you. Or gradient descent will calculate what is going to be the number to subtract it from here to result the 0 mistake. And then at the end of the day, you will just go there and you will see, Mike needs to return to me $2, and probably Alice shall return to me $4 because minus 4 is going to result 0. This is what calculated my gradient descent calculated. So if we will do it farther and farther, we will get into the 0. So you would see right now, if I will just make 500 epochs, we will get exactly 2. Oh no, we didn't. But probably if I will do 100, we will still no. What about 10,000? Still didn't. But anyways, this is exactly 2 almost. This is the good way. Knowing that the derivative has the limit, we will never get the 2. Sometimes we'll get, but right now we didn't. I mean, our limit is like infinitely close to 0, so it means that this number will be infinitely close to the target. And using this at the end of your gradient descent, you may say just round this number to get the exact number, and we will get -2, which is gonna result our loss 0. So when I'll apply this to here, you will see that our loss will become 0, and this means that this is the 0. I mean, this is almost 0 in the power of -30, which is like 0.00030 times and then 1 at the end. This is something like that, because we have the limit and our derivative always connected with the limits. So this is how we use our gradient descent. And in the next video, I'm going to explain you how to use the gradient descent in the neural network. Right now we used some dummy example with your friend, but I hope you got the point. Like, why shall we use this gradient descent? Like, when you have tremendous amount of iterations, you will never get out of these calculations. Like, there is just tremendous amount of time, so we need to have the algorithm which will calculate the mistake there. And of course, obviously, for this dummy example, this is just easy, so that we don't need to use the gradient descent here. But for the sake to explain it to you, I use this dummy example. But in the next videos, I'll show you not the dummy examples, but the real examples with the real neural network. And I already have this example in my channel. I will put link into the description. So I'll put smile there, so that you may distinguish that this is exactly this video, and you may watch it knowing that this is what is the gradient descent. Hope you got into this video. I hope this was helpful. Consider to subscribe to my channel, or don't consider anyways. Now, also you can support my channel in my description, and also we have a tutoring where I can tutor you mathematical concepts and mathematics according to the data science and the neural networks. I don't know why all the time I don't know why all this time I was watching my screen but not the camera. Also, we have the chemistry tutoring. This is my brother who is tutoring chemistry, and he is pretty much good in it. Right now, he studies in the some university, medical university in Thailand. Anyways, so he can help you with the chemistry, with the biology, because he is studying for the doctor, on the doctor or whatever. So I hope this video was helpful, and also if you need a tutorial or tutoring in the chess, also you can ask me. Thank you for watching this, and have a good day.